Hello and welcome to this recorded learning on 7 Series Memory Resources Part 1. My name is Frank Nelson. I'll be your instructor for this module. This module will introduce you to the 7 Series Memory Resources and highlight their features. After completing this module, you'll be able to describe the dedicated block memory resources in the 7 Series family of FPGAs. You'll also be able to describe the different block memory modes that are available to you. Recalling that this is a programmable memory block, it has different configurations that are possible. And you'll also be able to describe the capabilities of the built-in FIFO logic resources associated with each dedicated block RAM. So first, we're going to do a brief overview of the block memory resources. We'll get into the block RAM and the FIFO, and then in the second recording, of course, we'll wrap up with the FIFO discussion, and we'll look at various use models of the block RAM resources. Every FPGA design needs some memory resources. Now this is usually accomplished by the use of on-chip block memory, frequently called block RAM. Now the 7 Series block RAM is 36 kbits of true dual-port memory and is frequently used for FIFO construction, large data storage, finite state machines, as well as many other functions. Now the 7 Series devices also include dedicated hardware to convert each block RAM into a FIFO. The 7 Series devices have identical block RAM resources. In fact, they are also identical to the Virtex 6 block RAM resources, except for one or two minor tweaks. Now this makes design migration easy. The 7 Series block memory also includes a built-in pipeline feature to improve your speed to 600 MHz operation. This architecture also includes an output register that gives a faster output clock rate, but increases your system latency a little bit. The block RAMs also have 2 independent ports, so each port can have different read and write port widths, and each port can have its own clock and different read and write aspect ratios. The block RAMs also include a configurable aspect ratio functionality, which allows each block RAM port to have its own customizable width. This helps the memory lend itself to more applications and ensures efficient use of the memory space. For example, this means you can write to port A in bytes, plus use the parity bit, read from port A serially with no access to the parity bits, and also write to port B in 16-bit words plus 2 parity bits, and finally read from port B in 32-bit words plus use the 4 parity bits. So basically, there's a lot of flexibility with this configurable aspect ratio and how it allows you to customize your memory space. Now, each block RAM can also be configured as a true dual-port memory, simple dual-port or single-port configurations. Every block RAM is also cascadable, which means they can be connected together to make larger memories, or FIFOs, when connected using the dedicated routing placed in the same column of the block memories. Now there is also a Byte-Wide enable that is helpful for embedded designers that are targeting soft processor core microblaze that's available to our customers. Finally, the device includes dedicated Hamming error correction logic, commonly known as ECC logic, to fix bit errors. You should also be aware that the 7 Series FPGAs require a separate power supply to power the block RAMs. Now that feature is different from the Virtex 6 device family. Now this ensures proper operation if you're targeting the -1L speed grade of the 7 Series product family. The 7 Series block memories allow segmentation of the block RAM into 2 18 kilobit memories. The block memory cannot be segmented further than this. Now this assures efficient usage of the dedicated block RAMs to suit your application, which saves system power consumption and allows you to maximize your memory use. In general, this is a pretty useful functionality since it allows you to not waste the block RAM resources. However, it does encourage the user to make certain they take full advantage of the leftover block RAM. This means that you might have extra memory resources that you can use for finite state machines or use for FIFOs when transmitting data between unrelated clock domains, for example. So just make certain you try to think out of the box because you might have block RAM left over that you can use if you're creative. Now you should also note that unlike Spartan 6, the Virtex 6 and 7 Series block RAMs allow you to build a FIFO out of one of the segmented 18 kilobit memory resources. Now let's take a moment and look at a little more detail at the block RAM capabilities. Now as I mentioned, these block memories are true dual-port memories, even though in this slide we're just looking at a single-port configuration. This means you have a ton of flexibility, but you also need to make sure that you're driving the ports properly to avoid any problems. Now the ports available to you for single port configurations are listed here on this slide. Since the block RAM can be segmented into 36K or 18K bit sizes, you're allowed to build with the widest implementation of 72 bits on a single block RAM. This may require you to configure the block RAM as dual port and then use the two output buses as one 72-bit bus. If you had segmented your memory into two 18 kilobit blocks, you would be allowed to build at the 36-bit data width. This flexibility enables the user to double the memory bandwidth per block memory if desired. Now the block RAM not only allows you to customize the port widths, it also allows you to configure how the memory is written. You can select from write first, read first, or produce no change. Now all of these features can be customized by you when you customize your memory with the core generator GUI. This makes memory integration easier since the utility also makes an instantiation template for you to connect to the rest of your design. You should remember that read and write operations are done simultaneously and independent on both ports A and B. This means that each port has its own clock enable and write enable ports. You should also know that every write operation also performs a read operation. This means that you have the ability to select the operation or the block RAM you want to use. So you can perform a read before write, write before read, or not allow an output change from the block RAM when writing. It is also very important that you remember that you can perform a simultaneous read and write or a write and write to the same memory location. Both of these operations can cause data corruption, however, so you'll have to make sure that your address and control signals are stable and as you planned them to be during an operation so that you can avoid data corruption. The dual port functionality also allows the two clocks that can connect to the block RAM to be asynchronous to each other. Now this facilitates the block RAM's use as a FIFO a great deal. Most block memories are used for simple dual-port block RAMs. In this case, each port is assigned either a read or write functionality, which is the natural structure for FIFOs, which are very commonly built with block RAMs. Now you also should note that each port's maximum size depends on the size of the memory you're building. So if you build a 36K bit memory, your largest port could be 72 bits. Likewise, an 18K memory can build a 36-bit port width. Now parity bits can be used for parity generation, which is left to the user to encode into the initialization of the memory. But effectively, the extra bit width can be used for anything, since it's being stored in memory like any other bit. Now that's why each block is 18K bits, not 16K bits. So while there is no built-in parity checking logic, the extra space for you to store that bit has been allocated in the block memory's construction. However, you will still need extra logic to check that your data is accurate for the parity bit. This slide is showing you the supported port sizes for the block RAM resources based on your selection of the functionality for your memory, whether that is true dual port, simple dual port, or a single port memory. Now most customers just build the memory with the core generator and the GUI will provide you a list of the possible port sizes that are supported. So this helps you avoid making an unsupportable memory by having the core generator do some error checking for you. Now the 7 series block memories allow for 2 block RAMs to be cascaded together with the dedicated routing resources that runs between them. Now this is important because it enables you to preserve the timing, but is only allowed between only 2 neighboring block RAMs. So you cannot cascade more than 2 blocks either way. And note, if you're considering using the Spartan 6 device family, it does not have this cascade feature, but Vertex 6 does. If you want to build a larger memory that uses more than 2 block RAMs, you can still do this with the use of the core generator, but in that case you'll end up with multiple block RAMs connected together with some additional input decode and output multiplexer logic being built into the component. Now that means that extra CLB logic will be necessary in a large memory construction, and that will impact the memory's input and output performance. So for example, the core generator allows you to build larger memory arrays like the 128K, 256K, and 512K and larger memory arrays. But these, again, will include many more RAMs as well as lots of CLB logic in their construction, and likewise you can expect the performance to degrade some. The integrated error correcting logic, or ECC logic, corrects single bit errors on outputs. It can also detect, but not correct, double bit errors. Now this allows you to identify the address of the error whenever needed. This logic is dedicated in each block RAM and can be useful if you want to deliberately insert an error for testing purposes. Now this resource can also be used with external memory controllers built with the memory interface generator. That's the MIG, and that's part of the core generator. Now this is especially helpful when designers are building an external memory controller into the FPGA for use with a high-speed memory device. The 7 series family also supports the use of a Byte-Wide enable, just like the Virtex 6 device family. Now this is useful if you're building an embedded application with a microblaze soft processor core. The Byte-Write operation during your write first mode makes the bytes not being written to show an undefined value on the output. That way the output truly reflects the new memory contents. You also need to remember that writing always implies a read, so if your design is always reading data from the block RAM, you may need to alter your design to only read when the read signal is asserted. Now note, this will also save you power, so there's lots of good reasons to do just that. Now let's wrap up this module with a brief summary, and then you can listen to part 2 to learn more about the FIFO capabilities and how to use your block RAM resources in your design. In summary, the 7 series block RAMs provide the on-chip bulk memory required by many applications. Now this complements our distributed select RAM resources and the ability of users to integrate an off-chip memory next to the FPGA, in which the FPGA would contain your memory controller. So there's really 3 big pieces to the memory uses for customers. The use of a memory controller inside the FPGA to drive an off-chip memory, the use of the lookup tables to be reprogrammed as distributed RAM, which is small 16-bit or 32-bit memory spaces. And then there's finally the big chunk, which is the most common, which is the block RAM resources we've been talking about. Now this provides a huge aggregate bandwidth for each block RAM to support up to 2 72-bit ports as well on the configured block RAM. So a lot of flexibility and a lot of power built into the block RAM. This also supports this Byte-Write capability we talked about, the integrated FIFO logic, which we'll get into in the next recording. And we've also mentioned to you that it has an integrated error correcting logic that's dedicated to silicon as well. So a lot of great features, and we'll talk more about these features in the second recording. So let's start off with a brief discussion about the FIFO's capabilities. The 7 series also includes dedicated hardware to convert each block RAM into a dedicated FIFO. This is, of course, going to have better performance than a soft-core implementation of a FIFO, and will save you CLB resources since this logic is dedicated to the silicon. So if in the past you instantiated a soft-core FIFO, you're going to want to change that to a hard-core when you use one of the 7 series devices. Now the FIFO is full-featured and supports synchronous and asynchronous read and write clocks, so no phase relationship between the clocks is required. It also has full, empty, and programmable, almost full, and empty flags. The synchronous FIFO mode eliminates the uncertainty of flag latency inherent with asynchronous operation as well. It also has an optional first word fall-through option that enables the first word after the empty signal is asserted to be immediately available. The FIFO offers many configurations, just like the block RAM, and it even is available to a segmented memory. So if a block RAM needs to be segmented into 18 kilobit block, you can still use the dedicated FIFO hardware to convert that 18 kilobit block into a FIFO. You should note that the FIFO read port typically is associated with block RAM port A, and the write port is assigned to the block RAM port B. You should also note that when block RAMs are cascaded by connecting 2 neighboring block RAMs to make a larger memory, you can also make that memory into a 64K-bit FIFO. The FIFO supports the use of asynchronous clocks, which supports a standard or first word fall-through mode. This is selected by choosing the core's attribute of enable synchronous defaults, which is the default setting. Now the synchronous mode can be used in standard mode only. This allows deactivation of the flags, which enables lower latency. So it's up to you to decide how you want to program this FIFO. Note that neither mode requires any additional logic, and all of this can be assigned via the core generator when you build your FIFO there. The FIFO core also can generate numerous flags which are selectable by the user when you use the core generator GUI. Likewise, these flags do not require any additional logic, but there's support for a number of different FIFO status flags, including the full, the almost full, the empty, and the almost empty flags, which are pretty standard operation for any FIFO a designer may have built. There's also support for full and almost full flags, which are synchronous to the write clock, and also the empty and almost empty signals, which are also synchronous to the read clock. The FIFO core supports a first word fall-through mode. So in normal mode, the first word of data must be actively read from the FIFO. When the empty is deasserted, the read enable must be asserted to access that first word. In the first word fall-through mode, data appears on the read port as soon as it is pushed into the FIFO. The read enable signal will signal acceptance of that data on the data output. The mode is controlled by the first word fall-through attribute, which you can set with the core generator when you're building your custom FIFO. Now let's have a look at some of the use models and how to get access to the block RAM resources and add them to your design. Well, the first thing I want to point out is inference varies by synthesis tool. Now, XST and Synopsys tend to do the best jobs, and they tend to infer the simplest configurations of most hardware-dedicated resources, such as the block RAM. So the single-port, true dual-port, and simple dual-port RAMs can be inferred, but note not all features are going to be activated when you infer the resource. So your RTL code must describe the functionality of the desired RAM for it to be inferred properly. The RTL description must match the capabilities, so you need to be careful when constructing your RTL code. And this is especially important when you're using the synchronous write and the synchronous read functions, building one or two addresses being accessed on each clock and the synchronous reset being used for the output stages. Now there are synthesis directives, and these will vary by synthesis tools, and these will be used to guide the synthesis tool to infer the proper configuration of the memory. So if you're using XST, check out the XST user guide for both attributes as well as coding examples, or refer to your synthesis vendor's documentation to learn how to infer the block RAM memory or FIFO with that synthesis tool. Now keep in mind that there are specific directives for the type of memory you want to infer, such as when you are building either a distributed select RAM or a block RAM. Likewise, the coding style will vary by the resource you're targeting. Also note that if FIFO resources have limitations on their inference, but in the end, it's generally easier to just instantiate the component after customizing with the core generator and then add it to your design directly through instantiation. Now, instantiation can be done in a couple of different places. You can go to the Xilinx Unified Libraries Guide, which contains the basic rote simple primitives like you see here on this slide, the RAM B36E1 component, and as you can see, it's full featured. You just instantiate and connect up the ports the way you want, and the ports you don't connect up, then you simply don't get those resources. But you can also go into the core generator, which is a series of GUIs, so you can simply step through and select the options you want, and then have the utility build a netlist for the component. Finally, the core generator will also create your instantiation template for that netlist, so this makes adding the component to your design a lot easier. But if you do want to instantiate a component from the Xilinx Unified Library, you can simply go to the Language Template Utility, which is part of the ISE software, and you can find the component listed there and then simply instantiate it as you would like. On this slide, you see a screenshot from the core generator. As you can see, it allows you to select the type of memory with the block memory generator. Now, this simply allows you to customize all the functionality that you could possibly want for the component. And this utility has been built by Xilinx experts, so it readily supports all the new features of the newest devices. One of the nicest features is the utility will not allow you to build an unsupportable component for your chosen device. It simply does all the error checking for you before you have even finished building it. So if you've never worked with a core generator, I would encourage you to do so. Also keep in mind that simulation of the core generator components is also completely supported. So after building this memory, if you want to test it, you certainly can do so with your simulation tool. Okay, now let's wrap up this module with a brief summary about what we've learned about the 7 series memory resources. In summary, the 7 series block RAM provides, again, the on-chip bulk memory required by many applications. But the 7 series also supports distributed memory resources, which is the LETs reconfigured to actually build small pieces of memory, and also supports the use of memory controllers added to your FPGA design to drive an off-chip memory component. So the block RAM is a key part of that. It's your larger memory space embedded in the FPGA, and as I mentioned, it's dedicated in the hardware. Now, it provides a huge aggregate bandwidth, and each block RAM has up to 2 72-bit ports that it can support. So it has quite a bit of functionality built into it and quite a bit of programmability, which gives you a lot of flexibility on how the memory is used, whether it's used as a FIFO or block RAM, your port sizes, whether you're doing single port, dual port, etc. It also has the ability to support byte-wide capabilities, has an integrated FIFO logic that's also dedicated in the hardware, so that you waste no extra logic by converting your memory into a FIFO. It also has your integrated error-correcting logic that's dedicated to silicon as well. All in all, it's a lot of features, very good performance, a terrific resource. Well, there's lots of useful information about memories and memory controllers that can be found on Xilinx's website, support.xilinx.com. The 7 Series Memory User Guide provides very complete device information. All 7 Series users will probably want to refer to this document for the most silicon information when building a memory component. The 7 Series FPGA's Embedded Memory Advantages white paper is also helpful. It describes the resources at a high level and explains why you should care about the memory feature set. So this might help you guide you into targeting some resources that you're planning on using. If you would like to see what other course offering we have or what other free RELs are available, you can go to the Xilinx education link you see here. I would also like to mention again that there are other architecture modules available to discuss the basics of Xilinx's newest devices, the 7 series of FPGAs. You may find these useful, especially if you want to learn more about the differences between available FPGA products, say our Vertex 6 or Spartan 6 families. But whatever you do, please take a second, let us know what you thought of this RL. Just click on the icon at the end of the presentation and tell us what you thought. Again, my name is Frank Nelson. You've been listening to the 7 Series Memory Resources, Part 2, Recorded e-Learning. Don't forget to check out Part 1 if you haven't already, or check out some of our other 7 Series RELs. Thanks for your time and attention, thanks for listening, and thanks for your business.